Let's do something new today and learn WebAssembly. Before we get started with WebAssembly, we'll have to set up some ground explanations, or we all have to be on the same page as far as what machine instructions, interpreters are all concerned. All right. Now, when you get a processor is able to execute a set of instructions. These instructions are always in the binary format. They are not human readable. They're always binary. So a processor is able to take in binary instructions and is able to perform an output. Now over here, what I'm showing you is just a representation of what an output can look like. It can be a wall that turns on, a light that goes on, and so on and so forth. All right. But essentially, a processor reads binary instructions that are not human readable, processes them, and then outputs something. All right. An interpreter is a little bit different. An interpreter takes code that is human readable. There is a virtual machine interpreter that reads this line by line, or maybe just does some sort of pre-compiling, reads them line by line, creates the binary instructions on the fly, which are executed on the processor, which gives you the output. All right. Now, the obvious difference between a compiler and an interpreter, or a compiled language and an interpreted language, is that you have that you have that advantage. I mean, you have that speed advantage with compiled languages versus interpreted languages, which is why C is always and will always be faster than Python, for example. All right. Now let's look at what machine instructions look like. They are not human readable, like I said before. However, there is a stopgap between machine instructions and what a human can read. All right. And that's generally called as assembly code. Now I'm showing over here a sample of what assembly code can look like. All right. So this is something that humans can perhaps read, but assembly code generally is very long, and you'll have to write a lot of instructions just to execute very little amount of code. All right. Now there is a way to mitigate this. This is where higher end languages like C, C++, and Java and all come, but we'll visit that in just a second. Before we go ahead, let's look at how JavaScript itself is executed. And you will see that, whenever you have like a JavaScript code, there is a JavaScript compiler. The compiler creates something called as a bytecode, which is interpreted, which creates these binary instructions, and then they're executed on the processor. Now, this is actually a very simplistic view of how JavaScript is executed, but you can perhaps see how tedious this is, and you can perhaps see why JavaScript has a very high, performance overhead on it. All right. So how does WebAssembly work? WebAssembly is stored in something called as WASM files. This is analogous to .exe files in that they also contain binary instructions. Now, these binary instructions are executed directly on the processor, and the output of this is either requested by or sent to the browser. That way, this is faster than JavaScript than anything else. All right. Now, how are these WASM files created? Just like how you have a C compiler that can convert a .c file into a .executable file, you also have something called as a W2 WASM compiler. Now, a WAT file, a WAT file, essentially is a set of instructions that you can use to convert it into assembly. All right. So just like how we saw, what an assembly language is, which is nothing but a set of instructions, you can give the set of instructions in a .wat file, and using this compiler, it can be converted into a WASM file. All right. Now, understanding or remembering all of the assembly instructions is very difficult, which is why using something called as EmScripten or the EMCC compiler, it is possible to convert a lot of languages into WASM files themselves. All right. So in this case, EMCC can be used to compile a C program into .wasm file. All right. So this gives you the advantage of programming in something that you already know, converting it into a .wasm file, putting it onto the browser, and then executing it. So let's just see how to do exactly that. We'll start by installing EmScripten. This is done by doing the following things. The core EmScripten SDK, or called EmSDK driver, is a Python script. You can get it for the first time with the commands that you see on the screen. We'll first clone the Git repository. Next, we'll enter the directory. We'll fetch the latest version of the EM SDK, and this is of course not needed when you do it the first time. Let's download and install the latest SDK tools with this command. Let's also make the latest SDK active for the current user. And finally, let's activate the path and other environment variables in the current terminal. The link to the installation page is provided in the description. Let's write the simplest Hello World program in C. I have a simple C file called helloworld.c, which simply prints Hello World. Let's compile the program using the EMCC compiler. Once the command runs, you can see that it generates 3 files: a JavaScript file, a HTML file, and finally our WebAssembly WASM file. Here is what the generated HTML and JavaScript files look like. I'm going to try and execute this by simply dragging the generated HTML file and dropping it onto the browser. As you can see, this does not work. This is because WASM requires that the JavaScript files are loaded by a server. Therefore, I'm going to put this WebAssembly folder onto a virtual host and execute it from there. I've hosted the WebAssembly folder on localhost at port 8081. When I open the generated helloworld.html file, you can see what was generated by the EMCC compiler. The hello world statement from the printf is shown in the script text box. The hello world statement is also visible in the console. Let's examine for a moment the contents of the WASM file. To do that, I have installed the WABT package. Once installed, I used the WASM to WAT utility to convert my binary WASM file into a semi-readable WAT file. The output of this utility is redirected to a .wat file. As you can see, it is a bunch of code that looks more or less like a set of assembly instructions. These are hard to memorize and not nearly human readable, which is why we write our WebAssembly program in C. Now remember, it's not necessary to use the generated HTML file to see the output of your WebAssembly programs. We can write our own HTML or scripts. I'm creating my own HTML file here, and all I have to do is include the .js file generated by the EMCC compiler in the script tag. Now that we have written our own HTML file, let's see the result of that. You can see that the printf statement in the C program is written to the console log. Now that we've written a simple program, let's move on to a more complex example using WebAssembly. To do that, I'll create a new file called factorial.c. Since we now have to deal with writing our own functions and having them accessed via JavaScript, I need to include a header called EmScripten.h. The main function is pretty simple with just a simple printf statement. The factorial function must be declared with the EMCC accessor called EmScripten_keepAlive. Other than that, this is a pretty straightforward factorial function. Keen-eyed viewers will immediately see the logic error I have made writing this function. To compile, I'm going to use the EMCC compiler and pass the following flags. WASM should be set to true. The no exit runtime should also be set to true. We must also tell the EMCC compiler to export certain inbuilt methods. In this case, the C call to the JS file. As you can see, the output files are generated with default names. Let's correct that and add an option to output to factorial.js. I'm going to add the output option to the EMCC command. The output file will be called factorial.js. You can see that the output is generated to the factorial.js and factorial.wasm files. Alright, now let's write the factorial HTML file where our WebAssembly is executed. As you can see, this is pretty straightforward. All I have to do is include the EMCC generated factorial.js file. I'm also including a file here called execute factorial.js, which will ultimately make a call to our WebAssembly factorial function. Let's also add the button, which when clicked, will make a call to the WebAssembly's factorial function. Next, let's write the execute factorial.js file. When the page has finished loading, we'll add the click event on the button. This function will invoke the module.ccall function. Remember, this was one of those methods that we exposed when compiling. This method takes 4 parameters: the name of the function, the return type of the function, in this case it's number, and the types of arguments, which is also number, and finally the argument value itself. Once done, let's console log the result. Before seeing the results, I just wanted to let you know that I have corrected the syntax issues in the JS file. Once I click the Get Factorial button, you can see that the value is logged in the console. This is an error because the factorial of 5 is 120. This is because of the previously mentioned logic error in the C file. Let's fix that now. There was a problem with the looping here. Let's correct that. It's such a silly mistake to make. Alright. Once that's corrected, we can now see the corrected value logged in the console. Honestly, that's all there is to show about WebAssembly. Time to show my face and say my ending lines. That was WebAssembly in less than 15 minutes. I think this is our shortest episode yet. I hope you got something useful out of it. I know I did. So I'll see you again next week. Until then, be safe and keep learning.